Hello everyone and welcome back to my channel. Today I am going to talk about a topic that beautifully connects mathematics with medicine, drug assimilation. Now at first glance, mathematics and medicine may look like two completely different subjects, but in reality they are closely connected. Every time you take a pill, a syrup or an injection, a number of processes begin inside your body. The drug has to be absorbed, it has to circulate in your blood, and then it has also to be eliminated. Doctors and scientists must know exactly how these processes happen in order to decide how much medicine to give and how often it should be taken. And the tool that helps us to describe and predict these processes is none other than differential equation. Today, along with me, Arjun Singh and Uday Tyagi will try to teach this topic.
Let us begin with the basics. Whenever we take a medicine, three main stages happen. First, the drug is absorbed into the body. Second, it enters the bloodstream where it starts working and produces the desired effect. Third, the drug is eliminated by the organs such as the liver and the kidneys. The big challenge here is dosage. If the amount of drug is too small, it may not work at all. If the amount is too large, it may be harmful or even dangerous. So doctor must find the right balance. Since drug concentration is constantly changing with time, we need a mathematical tool that can describe continuous change. This is exactly what differential equations are designed for. They allow us to write simple relationships that describes how much drug is entering, how much is leaving, and what the concentration will be at any moment. Now let us look more closely at the process of drug assimilation. Suppose you swallow a pill. The pill first dissolves in the GI tract, which is basically your stomach and intestines. From there, the drug molecules are absorbed into the bloodstream. In the blood, the drug circulates to different parts of the body and produces its effect, whether that is reducing pain, lowering blood pressure, or causing sleep in the case of anesthesia. Finally, the body starts to remove the drug naturally. The liver breaks down the drug and the kidney remove it from the blood through urine. To make things simple, scientists use two compartment model. One compartment represents the GI tract and the other represents the bloodstream. Even though the real body is far more complex, this two compartment model is accurate enough to capture the most important features and is easy to analyze mathematically. Now we come to the mathematics. Let's begin with the GI tract. We denote the amount of drug in the GI tract at time t by x of t. Once the pill has been swallowed, no new drug enters the stomach. The only change is that the drug amount decreases as it gets absorbed into the blood. The rate of change of x of t is proportional to the amount still present. In mathematical form, this is expressed as dx by dt is equal to minus k1 x of t. Here, k1 greater than 0 is a constant called the absorption rate constant. When we solve the differential equation, the solution is x of t is equal to x of 0 e raised to minus k1t. This represents an exponential decay. It means that the amount of drug in the stomach decreases quickly at first and then more slowly as time goes on.
Now, let's model the bloodstream. We call the amount of drug in the blood Y of T. The blood gains drug at the same rate the GI tract loses it, which is K1 of T. But at the same time, the blood also loses drugs because the body is eliminating it through the kidneys and liver. The loss happens at a rate proportional to the amount in the blood, written as K2. The equation then becomes dy by dt is equal to k1x minus k2y. We substitute the value of x as a function of t in x naught e to the power minus k1t, and hence we get dy by dt plus k2y is equal to k1 x naught e raised to minus k1 t. Since we previously formed a differential equation which is of a linear form, then we use the integrating factor method to further solve the differential equation. This is slightly more complex than the previous model of the GI tract because it has both an increasing term and a decreasing term. But when we solve it, the solution shows something very realistic. The drug concentration in the blood first rises, then reaches a peak, and finally falls as elimination dominates. This matches real life perfectly. When you take medicine, it takes some time to kick in, then it works for a few hours, and finally the effect wears off.
Now, let's apply this knowledge to a real world case. Suppose a vet wants to anesthetize a dog for surgery using a drug. The guideline is that 45 milligrams per kilogram of body weight should be there for anesthesia. So, if the dog weighs 50 kilograms, the required amount in the bloodstream would be 45 times 50, which is 2250 milligrams. However, the drug does not stay constant in the body. It has a half-life of 5 hours. That means every 5 hours, the drug concentration in the blood reduces to half of what it was before. So the question is, what should be the initial dose of the drug so that after 1 hour, there are still 2250 milligrams present in the body to keep the dog under anesthesia. Let x be the amount of drug at time t. dx upon dt is equals to minus kx. And further, x of t is equals to x naught e raised to minus kt. So at time of 5 hours, x becomes x naught upon 2. So we can write x naught upon 2 is equals to x naught e raised to minus 5k. And further, we can write e raised to minus 5k equals to half. Now, value of k can be log 2 upon 5, which is approximately 0.1386. So the required dose at the time should be 45 into 50, which is 2250 milligrams. So at time of 1 hour, 2250 equals to x naught e raised to minus k, that x naught equals to 2250 e raised to k. Since e raised to k is approximately 1.149, 2250 into 1.149, which is 2585 milligrams. So a single dose of 2585 milligrams should be administered into the dog.
From this discussion, we can draw three important lessons. First, differential equations allow us to predict drug concentrations in the body over time. With just a few simple formulas, we can describe what is happening inside a complex biological system. Second, they are crucial for optimizing dosage. By using these models, doctors and researchers can ensure that patients get enough medicine to be effective, but not so much that it becomes toxic. And third, these examples show how mathematics and medicine are interconnected. Equations are not just abstract ideas from a textbook, they are practical tools that help in drug development, testing, and patient care every single day. To conclude, drug assimilation is a biological process, but mathematics provides the framework to understand it clearly. By modeling the GI tract and the bloodstream, we can calculate how quickly drugs are absorbed, how long they remain effective, and what the safe dosage should be. The example of anesthetizing a dog may look simple, but the same principles are applied to human medicine in areas ranging from antibiotics to vaccines and cancer treatments. This is the real beauty of applied mathematics. It transforms numbers and equations into knowledge that directly improves healthcare and saves lives. Thank you for watching this video. If you found this video informative and learned something from it, please like, share and subscribe. Your views are of the utmost importance for us because the number of views will directly correlate to the number of marks we get. Yes, this is for a maths assignment in our college. Thank you.